We have this circuit with an inductor in it. There's a 2 amp current source providing power to the circuit for t less than 0. So for t less than 0, this switch is in this position. Current goes through here, charges the inductor. For t greater than 0, the switch moves to position B and the source is isolated from the rest of the circuit. We have a number of things we want to find out about this circuit. The first one is the differential equation governing the current I sub L of t for t greater than 0. Always pay attention to what time you're working with. So if we want the differential equation for t greater than 0, let's sketch the circuit for the t greater than 0. So at t greater than 0, the switch is in this position, and this source is isolated from everything else. The rest of the circuit just looks like a couple of resistors, 2 kilo ohms, another resistor, 2 kilo ohms, and a 2 millihenry inductor. And we want to find the governing equation for I sub L of t. Now, since we need to write a differential equation, we're going to want the voltage-current relationship for the inductor, so let's label the voltage across the inductor in terms of its current. So that's the appropriate polarity. This is 2 millihenries, 0.002 henries, times the derivative of I sub L with respect to time. Now we've got the voltage-current relationship on our diagram, and we've got the appropriate sign convention. Now all we have to do is write KVL, KCL, and Ohm's law. It looks like if I do KVL around this loop, I need the voltages across the inductors. If I sub L is in this direction, then that means if I use that for my current in the 2 kilo ohm resistors, those are in that direction, and my voltage polarities are going to be plus, minus, plus, minus. So now, if I'm looping in this direction, I'm entering the positive terminal first, so I get 2 kilo ohms, or 2000, times the current, I sub L, plus entering the positive terminal here, another 2000, 2 kilo ohms, times I sub L again, and then entering the positive current on the voltage across the inductor, which is 0.002 DIL by dt. That brings us back to our starting point, so that's 0. So I have 4000 I sub L plus 0.002 DIL by dt is equal to 0. That's a perfectly legitimate differential equation governing I sub L. In the second part of the problem, we want to find the time constant from this given differential equation. Now, our standard form for a differential equation is going to be dy by dt plus 1 over tau times y is equal to 0 if the equation is homogeneous, which this one is. So what I want to do is get a 1 in front of the derivative term. So if I divide everything by 0.002, I have 2 times 10 to the 6th I sub L plus DIL by dt is equal to 0. So this is 1 over tau. So tau is 1/2 of a microsecond, or 1 over 2 times 10 to the minus 6th. Now we'd like to check our value for tau by determining what it is directly from the circuit from the inductance and the equivalent resistance seen by the inductor. So again, going back to this circuit over here with the source isolated from the inductor, we need to find Req. So remember, we're looking for a Thevenin resistance seen by the inductor, so take the inductor out, and the Req is the voltage-current relationship at the terminals of that. So we have 2 kilo ohms, 2 kilo ohms. KCL here tells us that these are in series, so Req is the sum of those, so Req is 4 kilo ohms. For an RL circuit, tau is L over Req, which is 2 millihenries, so 2 times 10 to the minus 3rd henries over 4 times 10 to the 3rd ohms, which is 1 over 2 times 10 to the minus 6, which is 1/2 of a microsecond. Those match up, so we're all happy. Next, we want to find the initial condition on the inductor current. So we want to find I sub L at t equals 0 plus just after this switch is moved to position B. So to determine this, we rely on the fact that inductors cannot change their current instantaneously. So if we set up the circuit at t equals 0 minus, just before the switch moves, Our 2 amp source is connected to the inductor through this switch. There's a 2 kilo ohm resistor here. There's a 2 kilo ohm resistor here. And now we'll assume that the switch has been in position A for a long, long time. That means that with a constant forcing function, the inductor current is going to be constant because we'll be looking at the particular solution to a differential equation with a constant input. So the inductor looks like a short circuit. And this is I sub L at t equals 0 minus. This circuit we can solve. It just looks like a current divider. So I sub L at t equals 0 minus is 2 amps times the other resistance, 2 kilo ohms, over 2 kilo ohms plus 2 kilo ohms, which is just 1 amp. Now we can invoke the fact that this current cannot change instantly. So I sub L at t equals 0 plus is the same as I sub L at t equals 0 minus, which is 1 amp. Now we want to find the actual current through the inductor as a function of time for t greater than 0. We know that this is a homogeneous differential equation. So the form of the solution, I sub L of t, is going to be some initial condition e to the minus t over tau for t greater than 0. So I0 is 1, e to the minus t over 0.5 microseconds for t greater than 0. Now let's look at the resistor current, I sub R of t, at t equals 0 plus and t equals 0 minus. So at t equals 0 minus, this circuit over here is the one we use. We have a 2 amp source, 2 kilo ohm resistor. This is I sub R at 0 minus, another 2 kilo ohm resistor. And again, at t equals 0 minus, if we assume that the switch has been in position A for a long time, this inductor is going to look like a short circuit, and this is I sub L at 0 minus. Now this is still a current divider. So I sub R at 0 minus is going to be 2 amps times the other resistance over the sum of the two, which is half, which is 1 amp. And that's a darn good thing because I sub L is 1 amp, I sub R is 1 amp. We have 2 amps going in here. If we do KCL at this terminal, everything matches up. Finding the resistor current at t equals 0 plus is a little bit of a problem because we don't know anything about how the resistor is going to be behaving. It doesn't have to have continuous currents. Its current can go from one value to another without any intermediate value being involved. So at t equals 0 plus, we have to sketch the circuit again. The 2 amp source is isolated from the circuit, so it doesn't matter anymore. There's a 2 kilo ohm resistor here, 2 kilo ohm resistor here. This is I sub R at 0 plus. Our inductor looks like an inductor now, but we do know that this is going to be I sub L at 0 plus, and since this can't change instantly, we know this is 1 amp. So if we do KCL here, we say that I sub R at 0 plus I sub L at 0 plus, assuming that positive currents are leaving the node. So I sub R at 0 plus is going to be negative 1 amp. So it can change all over the place from 1 amp to negative 1 amp in no time at all.